இதுதான் லாஸ்ட் டாபிக். ஒரு 5 minutesல இது முடிஞ்சிடும். ஒயிட் நாய்ஸ். So this is the ideal form of noise. This is the ideal form of noise. I am just writing the properties of white noise. This is the ideal form of the noise. Again, usually we will use for mathematical analysis. Ideal form of noise. It has power spectral density over wide range of frequency. It has power spectral density over wide range of frequency. Okay. Again, this is somewhat similar to the thermal noise. Already we have seen this property is similar to thermal noise. Okay, so white noise is the ideal form of the noise. It has power spectral density over wide range. Again, I already told you it is similar to thermal noise. That means it will have flat power spectral density. It contains all frequency component in equal. It contains all frequency component. It contains all frequency component in equal. That means power spectral density is flat. That is, power spectral density is flat from minus infinity to plus infinite. These are all the basic properties of white noise. And mainly, what is the major difference between the white noise and the thermal noise? Okay, whenever we discuss about any generalized system, that time we will use the white noise definition. That is mostly for mathematical analysis. It will be used in the mathematical analysis for the communication system. Used in math analysis of the communication system. Okay, we will consider as a white noise is the generalized noise. Okay, here I am not mentioning white noise is from where it is coming. I am not mentioning. It is like a generalized noise, white noise. These are all the properties of white noise. So now this white noise, generally noise is random. Okay, whether it may be white noise or some other noise is always random. So noise means always random in general. That means in time domain we do not know what is the actual contribution due to the noise at each and every time. In general, that is random. But we can write even for random. That means even for noise signal, we can write what is the autocorrelation for noise also. That is Rxx of tau. Then what is the power spectral density? Sx of f. Now I know what is the power spectral density for white noise, because power spectral density of white noise is somewhat similar to the thermal noise. Okay, so what happens? The power spectral density here also it is like uniform. That means it is going from minus infinity to plus infinite. Okay, the power spectral density, and then again it is having power spectral density value as n naught by 2 because two-sided. So power spectral density is n naught by 2. This is Sx of f. So once I know power spectral density, I can calculate what is the autocorrelation function. Using the inverse Fourier transform. Please use inverse Fourier transform to calculate the autocorrelation function. Okay, for that particular noise, already I know the power spectral density. Okay, so now what is the autocorrelation function? Again, you can refer your basics of Fourier transform. For constant signal, if you take the Fourier transform or inverse Fourier transform, constant in one domain will become like a impulse in the other domain. Please remember this concept. Already it is available in the signals and system. Constant in one domain will become like a impulse in the other domain. So at the frequency domain, we are having constant value. So that means we will have impulse value. At the tau domain, at the time domain, that means tau domain, with the value of what? So with the value of n naught by 2 multiplied with del tau. Okay, this is the impulse value with the strength of impulse is present at a tau. Tau is equal to 0. You know, impulse is always present at a t is equal to 0, or here tau is equal to 0. But what is the strength of the impulse? The strength of the impulse is same as the what is the constant value present in the frequency domain. Okay. Again, if you have doubt, you just take the Fourier transform of this one. You know, Fourier transform of impulse is always 1. Then only n naught by 2 is there. So simply you will get n naught by 2. Again, this n naught by 2 is independent of frequency. Fourier transform means you are in the frequency domain. Okay, along with n naught by 2, you are not getting anything. That means n naught by 2 is constant for all frequencies. So what I'm telling, power spectral density is constant means you can calculate, you can apply the inverse Fourier transform, then you will get the impulse signal at the tau domain. So now I know what is the autocorrelation function for the white noise, that is n naught by 2 del tau, or if it is a power spectral density, that is n naught by 2. So in the exam, you have to be very careful in white noise with respect to white noise. They will ask either autocorrelation or power spectral density. Again, you should not get confused. If it is autocorrelation function, definitely that n naught by 2 has to be accompanied by del tau. If it is power spectral density, directly you can write n naught by 2. So you have to be very careful. Maybe both may be looking same, but there is a little difference with respect to del tau. So the same thing we'll write in terms of the equation. So for white noise, what is Rxx of tau? The autocorrelation function of white noise is n naught by 2 del tau. Then what is the power spectral density for this white noise? Okay, that is simply n naught by 2. So, and one more thing you can observe in this expression. Okay, you take this expression. Okay, finally, in this expression, if you put tau is equal to 0, what you are getting? Rxx of 0 is equal to n naught by 2. You are getting something when you put tau is equal to 0. But when you put tau is equal to other than 0, you know from the basics of del function, if you put any other value, say other than 0, Rxx of tau not equal to 0, definitely the value is 0. Okay, see, in the diagram itself you can observe. It is having value only at t is equal to 0, tau is equal to 0. For all the other value, that is 0. That means whenever we have a white noise signal, okay, white noise, whenever we have a white noise, okay, white noise in general is a random. So that white noise, it will have perfect correlation only when tau is equal to 0. See, I already told you, you take any signal, it may be random or deterministic signal, definitely at tau is equal to 0, there must be correlation. Again, what we are proving, in general, other than tau is equal to 0, the correlation may be there or may not be there in general. But here for white noise, when tau is equal to not 0, definitely there is no correlation. That is the important observation. With respect to the white noise. Okay, white noise correlated only at tau is equal to 0. It is correlated. Not only white noise, any signal is correlated at tau is equal to 0. But if tau not equal to 0, no correlation. That is the important observation with respect to the white noise. That means it is completely randomness. Random. Okay, so that is the one of the important properties of the white noise. So almost நம்மளுக்கு random processல கொடுத்திருந்த எல்லாமே வந்து கவர் பண்ணிட்டோம் with respect to the exam. Then இதை பேஸ் பண்ணி ப்ராப்ளம்ஸ் இதெல்லாம் சூஸ் பண்ணி அடுத்த கிளாஸ்ல பிகினிங்ல we will solve problems based on the random process. இதுக்கு முன்னாடி இருக்கிற கேட் எக்ஸாம் இதெல்லாம் கேட்ட ப்ராப்ளத்தை ஃபியூ ப்ராப்ளம் வந்து நம்ம சால்வ் பண்ணுவோம். அதுக்கப்புறம் நம்மளுக்கு கொடுத்துருக்கிற அடுத்த டாபிக்ஸ்க்கு போகலாம். அடுத்த டாபிக் வந்து நம்மளுக்கு டிஜிட்டல் கம்யூனிகேஷன் அண்ட் தென் இன்ஃபர்மேஷன் தியரி. ஸோ ஓகே, போத் ஆர் இண்டிபெண்டன்ட் டாபிக் ஒன்லி. எதை ஒன்றாலும் ஃபர்ஸ்ட் பார்க்கலாம், ஒன்றும் ப்ராப்ளம் இல்லை. ஸோ ஏதாவது ஒரு டாபிக் நம்ம அடுத்த கிளாஸ்ல வந்து பார்ப்போம். எதர் இன்ஃபர்மேஷன் தியரி ஆர் டிஜிட்டல் கம்யூனிகேஷன்.